There we go. All right, welcome back, and we shall resume our lecture here. Okay, so we talked about z-scores. So z-scores is the number of standard deviations a point is above or below the mean. And again, a standard deviation is a measure of spread, but it also because it tells us how clumped together or how spaced out the points are, we can use it to compare relative locations of points, and that's why this z-score thing works. And we can look at z-scores to make comparisons between these people's performances and say this one was more impressive than some other score. Okay, so read what the book has to say about z-scores. Also, the book will just touch on a few things and go into a little bit more depth than what I can cover in our class time here. But so the reading is always important. Okay, but I need to take a small break, and before we get into the normal model, which is really the important concept we need to cover, is I have to talk a little bit about shifting and rescaling data, okay? Shifting data and scaling data. Okay? So shifting data is the idea of adding or subtracting a constant number from all of the data points. So this is okay, so we can imagine maybe we look at the weight of people, okay? Okay, and we look at I'm going to just draw a very, very rough histogram, okay? Let's say we looked at the weight of some people, and let's say it was right skewed like this, okay? So, and let's say the I don't know, this is in kilograms, so we've got 50 kilograms, and it extends up to 100 kilograms out to 150 kilograms or something, okay? Shifting data would be, we could just add or subtract a number to this. So we could say, if this is what the weight of maybe 200 people look like, okay, the distribution of 200 people's weights, we could ask, what is the distribution of these 200 people's weights if they all carried 10-pound bricks, okay? And then we would just see that everybody's weight would just shift up 10 pounds, or in this case, 5 kilograms or whatever, and we would just shift everybody's numbers up 5 kilograms. Or we could say the recommended weight for this population or this group of people is 75 kilograms. And we could say, instead of looking at the raw weight, we could say the difference between their weight and the, quote, recommended weight. And so all this would do is this would just shift the data, okay, and we would just subtract 75 from all of these points, and we would be over at negative 25 down here, okay, and everything would just be shifted over, and it would still retain the same shape. It's just everything has shifted over the same distance because we're applying the same number to all of these points. We've just shifted everything the same distance, okay? So shifting, okay, and I hope I have space for this. Shifting only affects measures of position. So measures of position. Okay, so position are things like the center, the quartiles, the minimum, and the maximum. So I'm going to just list these off right here, but I'll say the mean, the median, the quartiles, Q1, Q3, and the minimum and the maximum, okay? Shifting does not affect measures of spread, okay? Because everything has shifted the same amount, how far they're spaced out from each other has not changed, okay? Because we've just moved everybody together, whether they're clumped up together or whether they're spaced out has not changed. So shifting does not affect spread. So maybe I'll also write that. Yes? Okay, so let me just write, shifting does not affect spread, okay? All right, so measures of spread are things like the IQR, the range, and the standard deviation. Those are the measures of spread, okay? Measures of position, those tell you where the center is. They tell you where the smallest point is. They tell you where the 75% is, 75th percentile is, or the 25th percentile is. Those things change, okay? But they don't change the spread because they've all shifted together, okay? Scaling data, on the other hand, so shifting is we're adding or subtracting a constant from all of the data points. Scaling is we're multiplying or dividing by a constant. So this is like going from inches to centimeters, or Fahrenheit to Celsius. We're multiplying. Well, actually, Fahrenheit to Celsius involves shifting and scaling. Okay, but going from inches to centimeters, we just multiply our numbers by 2.54 centimeters per inch, and so that actually changes where things are positioned and also how far they're spread out, because now we're saying things that were just 1 unit apart are now 2.54 units apart. Okay, and so the underlying data has not changed. The overall shape of the data has not changed, but we're changing kind of the spacing in between it. All right, so this is as if you can imagine if we had our distribution look like this. Okay, you can imagine this being on a piece of rubber. Okay, and we either stretch out the rubber and make everything wider, or we could compress the rubber and the graph becomes smaller. So if we compressed it, everything just becomes a lot more narrow, like this. Okay, or it could end up becoming much wider. All right, this is. Okay, the overall shape has not changed. The underlying data has not changed, but we've scaled it. We've either compressed it or made it wider. Okay, so shape does not change. I don't want to say size, but I don't know, just scaling. I got to stick with the term scaling, okay? Because size you might confuse this for the size of the number, and that's I don't know. Okay, all right.
The same as rescaling data, it says in the book. It doesn't really show
Does it say rescaling? Okay, that's what I mean. All right, scaling or rescaling. All right, it's the same. Okay. And yes, so this is these affect both measures of position and spread. So measures of position. So all of these that we've listed, the measures of position and measures of spread. So those are things like the IQR, the range, and the standard deviation. Yeah, my handwriting is getting sloppy, but okay, I'm just going to push this board up. Okay, so any questions on shifting or rescaling data?
Position measurements by whatever you're scaling the rest of it by, and have that be the same.
Okay, I'm sorry.
So if you're going from inches to centimeters, for instance, if you have already determined what the median, the mean, and all the other measurements are, can you just multiply those measurements by that?
Yes. So if we're going from inches to centimeters, and we find that the mean of this thing is 10 inches, okay, and we want to go to centimeters, the conversion from inches to centimeters is 2.54 centimeters per inch. So we just do 2.54 times 10, and we get 25.4 centimeters. Yes, you can do that. Okay, and that's fine. So whatever, but let's say we found that the standard deviation is is 3 inches. Okay. If I said this, we take the height of everybody and we say the standard deviation of the heights is 3 inches, okay? And I say, all right, now everybody's going to wear 6-inch heels, okay? Or 6-inch platforms, all right? And then we take everybody's height, okay? And we might say, okay, the average height before was 5'6", all right? Now that everybody's wearing 6-inch heels, the average height is now going to be 6 feet, right? We added 6 inches to 5'6", and we get 6 feet, okay? But if the standard deviation before was 3 inches, if everybody now wears 6-inch platforms or 6-inch heels, okay, the standard deviation is still going to be 3 inches. So the shifting, everybody's height has shifted because they're all now wearing platform shoes, but the spread has not changed, okay? And so, yes, you can just apply these changes. You can say, all right, the mean was 5'6", so we're just going to add 6 inches to that. That's fine, okay? But you don't want to take the measure of spread, the standard deviation, and then suddenly add 6 inches there either, okay? Okay, so now that we have shifting and scaling data, now we can start getting into the normal distribution, okay? And we will come back to this shifting and scaling, but this is kind of like a little break, little aside. I'm going to get into the normal distribution, and then we'll bring the shifting and the scaling back into this. Okay, so the normal distribution. Normal distribution, or sometimes the book says the normal model, okay? And that's, either thing is fine. This. All right. Okay, so the normal model will always have this shape. It's unimodal and symmetric, perfectly symmetric. Okay. unimodal and symmetric. This down here is supposed to be a perfectly straight line. Just I'm working on trying to draw straight lines here. Okay, so the center of the normal model, this is the mean. It also happens to be the median. Okay, so the mean and the median are both right here in the center. Okay, and that is given by the symbol mu. This is the mean, and it's also the median. That is the center. Okay, so when we're talking about a distribution, we've got the shape, unimodal and symmetric, the center, which is the mean mu, and we've got to talk about the spread, the standard deviation. And the spread is denoted by the Greek letter sigma, and that is the standard deviation. Okay, so on the normal model, the standard deviation okay, if you go out one standard deviation, so this distance is about one standard deviation, and this is one standard deviation. Okay, if we go out one standard deviation in each direction from the mean, so we start off in the center, we go up one standard deviation, we go down one standard deviation, inside this zone here, okay, we contain about 68% of the data is included within one standard deviation here. Okay, so underneath the bell and inside these bars here. Okay, that's one standard deviation above and one standard deviation below. That contains about 68%. Okay. If we go out two standard deviations, okay, two standard deviations above, two standard deviations below, now within this bell, okay, all the way across from here to here, we contain, about 95% of the data. So 95% of the data is contained within two standard deviations. So we've gone one standard deviation out, a second standard deviation out this direction. We go another standard deviation out this way, and another standard deviation out that way. So we go out two standard deviations in that direction. We contain about 95% of the data. Okay? And finally, if we go out three standard deviations in each direction, okay, we contain within three standard deviations almost 100%, not quite 100%, because there's still this tiny minuscule amount that's remains outside. Okay, there's still this tiny minuscule amount, but almost 100%, 99.7% of the data is within three standard deviations out in each direction. Okay, so here I've just talked about the normal model, and we're going out standard deviations in each direction, but what does this all mean? Okay, so let me try using an example from real life that I hope makes intuitive sense when we try this out. Okay. Okay. Oh well, before I get into this, all right. So the normal model is always going to be unimodal and symmetric, no matter what the mean or the standard deviation is. Okay, and so if we have a very small standard deviation, that just means our data is very clumped up together, very tight, okay? But it's still going to have this exact same shape, and it's still going to be ruled by this 68, 95, 99.7 rule, okay? And so if we have a tiny standard deviation, our normal model looks something like this, okay? It's just all the data is clumped up together. Our mean is still right here in the middle, okay? And if we go out one standard deviation, we might go out here and here, okay? So our standard deviation, our sigma, this distance is a lot smaller, but we still have 68% contained within one standard deviation above and one standard deviation below the mean. And if we go out 2 standard deviations, we still have 95%. And if we go out 3 standard deviations, we still have 99.7% of the data, okay? We just have a smaller standard deviation, a smaller sigma value, and it just means the data is compressed, okay? So that's just like rescaling the data, and we put it on the piece of rubber, and we've just crunched it up to be real small there, okay? And likewise, if we had a very large sigma, okay, a very large sigma, this just means our thing is much wider, okay? We're still centered at the mean, and we go out 1 standard deviation. This is going to be still 68% is contained within 1 standard deviation, and then we go out 2 standard deviations, 95%. This time, well, that's all crashing into each other over here, okay? But we've got 95% within 2 standard deviations. And then, I don't even know if I could fit it on the board, but if we go out 3 standard deviations in each direction, again, 99.7. And this one, it's just, we've stretched it out a lot wider because we've got a much larger sigma for this one, okay? But the overall idea of the normal distribution still holds, okay? Unimodal and symmetric has this exact shape, and the proportions and the distances from the means, all of this holds, okay? And so this is known as the 68, 95, and 99.7 rule, okay? All right, and these numbers, 95 and 68, these are approximations, okay? If we go out exactly 2 standard deviations and we draw like razor-sharp cutoff lines, it's going to be just slightly different from 95%, like 95.06 or something, but a little bit different, okay? So just be aware of that. Okay. All right. So let me draw a normal model using what kind of makes sense from real life. Okay. And so. All right. So human height is normally follows the normal model, okay? And so, well, and especially if we isolate it to either males or females, okay? If we include both males and females, it's a little bit off, but if we just isolate it and just look at one sex and we say, what is the distribution of male heights, that follows the normal model quite closely, okay? So the mean height of males is about 5 foot, for the United States, is about 5 foot 9.5 inches, okay? That's the mean, and that in inches, that's going to be 69.5 inches here, okay? The standard deviation is about, it's a little bit different, but just for simplicity's sake, we're going to say 3 inches, okay? It's a slightly different, but just so our numbers can stay clean on the board, we're going to just round down to 3 inches. It's close enough to give you guys the idea here, okay? So again, the center we put at 69.5 inches, so that's 5 foot 9.5, okay? So if we go up 1 standard deviation of 3 inches, it's going to take us to about here and about here. Maybe my 2 sides aren't perfectly equal. But if we go out 3 inches this direction and 3 inches in this direction, this takes us down to 66.5 inches, or 5 foot 6.5. And over here, this takes us to 72.5, or 6 feet and 1/2 inch. And this says about 68% of US males are between 5 foot 6.5 and 6 foot and 1/2 inch. Okay? And I think intuitively this makes sense with our experience of how tall other males are in the United States. Okay? And if we go out another standard deviation, this takes us down to 5 foot 3.5 inches, or 63.5 inches. And this takes us up to 75.5 inches, or 6 foot 3.5 inches. Okay, and that says %95 of US males are between 5 foot 3.5 inches and 6 foot 3.5 inches. Okay, and so yes, there are people who are taller than 6 foot 3.5, or I mean, there are males who are taller than 6 foot 3.5, and yes, there are males who are shorter than 5 foot 3.5, but only about 1 in 20. Okay, about 1 in 20 fall outside of this range. Okay, so about 95% are contained within the range. And then finally, if we go out another standard deviation, we're at 5 foot and 1/2 inch. And then over here, we're at 6 foot 6.5 inches. And this says 99.7. Okay, 99.7% of US males are between 5 foot 1/2 inch and 6 feet 6.5 inches. Okay, and so yes, we do have there are men who are shorter than 5 foot and 1/2 inch, and there are men who are taller than 6 foot 6.5 inches, but they account for only about 0.3%. Okay, 3 in 1,000 are taller than this range. Okay, and I think this makes intuitive sense with your judgment for the most part, I hope. Okay, and so this is the model for heights of U.S. males' height. Okay, and if we went to a different country, like the Netherlands, for some reason, for one reason or another, people from the Netherlands, the men at least, are taller on average than the United States. Okay, and I think their average height is like 5'11" or something like that. And then if we were to go to like an Asian country, on average they're shorter than the United States, and so I think their average is like 5'7" something or something like that. Okay, and so their normal model would be different. Okay, and we can't just take the normal model for U.S. male heights, and take this over to China and say, oh, you guys follow 99.7 are going to be contained in this range, and you're not going to have that. Okay, but within the United States, this is approximately right. Okay. It might be both, right? So if we go to another country, we'll definitely have to shift the center, okay? And we might have to rescale it, so if their standard deviation is different, okay? If their standard deviation is different, we'd also have to do some rescaling. But we might be able to make some comparisons after we do the proper shifting and rescaling, and say, we might be able to compare someone and say, what's more unusual, seeing someone who is 6'3" in the United States, or someone who is 6'5" in the Netherlands, or what's more unusual, seeing someone who's 5'3" in the US or seeing someone who's 5'0" in China. Okay, and we can start making these comparisons if we know the proper numbers for shifting and rescaling. Okay, and the way we do that is by using our old friend, the z-score, and what we have about shifting and rescaling. And so actually, when we calculate a z-score, we're actually doing both the shifting and the scaling, whether you know it or not. We've done both shifting and scaling when we calculate the z-score. So again, going back to z-scores, the definition of the z-score is we've got, hang in there, all right? Y minus mu divided by sigma, okay? When we've subtracted the mu from every data point, that is the shifting part. We're subtracting a constant from everybody. That's the shifting. And then when we divide, or basically multiplying by 1 over sigma, we're basically dividing by sigma, we're dividing by constant. That's the rescaling part, okay? And so when we go to a z-score, what we're actually doing is shifting and rescaling. So the center is at 0, and the standard deviation is 1. Okay, and that's what we're doing when we find a z-score. Okay, and this is actually very handy because even though we might know that 68% are between here and here, and 95% are between here and here, if I said, you know, someone is 6'2", what percentile is this person? We don't know it right off the bat. Okay, if we said, you know, what percentile is someone who's 6'2", we don't know that answer right off the bat. So let's ask this question. Is let's say a male, a U.S. male, okay, who is 6 foot 2 inches. Okay. All right. And so when we're asking for percentiles, we want to know what percentage of people is this person taller than, right? When you get a percentile on your tests, it says you've scored better than, you know, 80% of the world or whatever. Here we want to know what percentage of people is this person taller than, okay? So in other words, we've got the distribution of heights. This is centered at 69.5 inches, or 5 foot 9.5, and this person is 6 foot 2, so that's 74 inches. So 74 inches is taller than 69.5. So this person is at 74 inches. So here's the cutoff point, and we want to know what percentage of people is he taller than. So we want to know what is the area over here, okay? This represents the percentage of people that he's taller than. And so we want to know what is this percentage here. Okay. So the way we're going to do this is we're going to change our height to a z-score. And a z-score is basically the number of standard deviations above the mean someone is, okay? And so we go to a z-score. So the z-score is the number of standard deviations someone is above the mean. So we take 74 inches. So again, our z-score is y minus mu divided by sigma. So we put 74 is our y. Our mu is 69.5. And our sigma is our standard deviation of 3 inches. So this becomes 4.5 divided by 3. Oh, did I? Okay. Yeah, and this is equal to 1.50. So this is our z-score. Okay. So that's great. So we've got the z-score, 1.50. It still doesn't tell us what percentage 1.5 z-scores is higher than, okay? However, we have something called a z-table in the back of the book, all right? And this is in like Appendix D, page A58, okay? In the back of the book, we have a z-table. So I'm going to, and I'll try to draw what the z-table kind of looks like. And you have 2 pages to the z-table. It's a really big table, okay? You've got numbers along here, and it starts off at 0.0, 0.1, 0.2, so on and so forth, okay? All the way down to 3.9 or something like that. Okay, and across the top you have 0.00, 0.01, 0.02, all the way over to 0.09, okay? So I have to take a break and talk about how to use this z-table, okay? So the way you use the z-table is if you have a z-score, the table, if you look up the z-score, it will return the area to the left, okay? So in this case, we want to look up the value 1.50, so we go to the row 1.5 and the column 0.00, and the intersection of 1.5 and 0.00 is 0.9332. Is 0.9332. Okay? Yes, we have a question.
Can I just ask how you chose the 0.00?
Yeah, it's because it ends 1.50, okay?
Oh no, I mean I get the 1.5, but why did you stop at the first?
Yeah, and so I'll explain this in a second here, okay? So that's for the number 1.50, okay? Let's say we wanted to look up the number, I don't know, 1.16, okay? We have to first go to the row 1.1, then we go over to the column that's 0.06. Okay, so we go to the column that's 0.06, and the intersection of 1.1 and 0.06 is the area to the left of 1.16. So in this case, 1.1 and 0.06 is 0.8770. Okay, so the area to the left is 0.8770. If we wanted to look up 0.24, we go to the row 0.2 and the column 0.04. We find the intersection of 0.2 and 0.04, and we get 0.5948. Okay. The same thing for negatives. So if we wanted to look up negative 2.13, okay, we go to the negative 2.1 row, and we go to the column that says 0.03. All right, is this okay, how I'm getting the intersection here? Okay. So we go to negative 2.1 and 0.03, and we get 0.0166. Okay, and again, all of these numbers it goes from a z-score to the area of the left. So it's just like this picture. If we change to a z-score and we were to just draw a cutoff line, and we want to know what is the shaded area to the left of that cutoff line, the table will give it to us. So in this case, we have a z-score of 1.50. We looked up 1.5 and 0.00 to get that number. We get 0.9332. So this tells us that to the left of this cutoff line, the area here is 0.9332. So what percentile is a male, U.S. male who is 6'2"? 93.32 percentile. Exactly. Okay. Now, sometimes you don't want the percentile. Sometimes it's like, I don't know, what percentage of people is taller than 6'2", or what percentage of people is taller than 6 whatever, okay? And you want the other side. You don't want the area to the left, but you want the area to the right, okay? The table will always give you the area to the left. There's nothing you can do about that. However, we know that the total area underneath the curve adds up to 1.0. Always, okay? The total area under the curve will always be 1.00. So if we know the cutoff, this cutoff value, if we know the area to the left is 0.9332, we can do 1 minus that to find the area to the right. So if we do 1 minus 0.9332, we get 0.0668, 0.0668, okay? And then we can say, all right, if the question was what percentage of males are taller than 6'2", that answer would be 6.68% of males are taller than 6'2". Okay, so what percent? Okay, and the answer is 1 minus 0.9332. Whoops. Is equal to 0.0668 or 6.68%. Okay, so here we've gone from the area to the left. So let me just get rid of these other numbers that we looked up. But we've gone from the area to the left to the area to the right just by subtracting that value from 1. Okay. Yes, we have a question.
The question you're asking initially, what percentile is U.S. male who is 6'2", that's not answering the question, what percentage of the U.S. in terms of male are 6'2". It's just answering how many are 6'2" and below, right?
Yes, yes, and that's the definition of percentile. Percentile is what percentage of people are this value or lower. Okay. And yeah, it's not asking what percentage of people are exactly 6'2". Okay, and exactly 6'2", technically, there's zero people in the world are exactly 6'2". If you could imagine the most precise ruler in the world, where we're saying you have to be exactly 6'2.0000000 inches, nobody's going to actually measure that. They'll always be off by even the slightest amount, okay? But that's just a very fine technical point that don't concern yourself with. Yes, we have a question.
For tests, will you be providing things like Z?
Yes, of course. I will have the Z table. That'll be it'll just be a photocopy of these pages at the back of your test. Okay, I'm not. This is not a class in memorizing 1,000 numbers here. Okay, that would be ridiculous. Okay, but so we can, if things follow a normal model, we can start asking more questions. All right. Things like, so we know what percentage of males are shorter than 6'2". Okay. We could ask. We might ask what percent is between I don't know, 5'6" and well, let's I don't know. Let's change this to I don't know, 5'4" and 6'2". Okay, I don't know if that even matters. Okay, so this is like this is a problem that NASA had when they were making these astronaut suits. Designing an astronaut suit is really, really expensive because it's got to be safe and protect you from space. And but they want to accommodate as many people as they can. But trying to design it's, you go to the store and you can buy a small, medium, large shirt, and that's fine. But trying to design a small astronaut suit, a medium astronaut suit, and a large astronaut suit is not as easy. And so they had to try to figure out, well, if we make one astronaut suit that fits all, how many people can we accommodate without being too big for the little people and too small for the big people? And so they said, all right, well, I'm just making up numbers here, but they said, okay, well, if our astronaut suit can fit 5'4" to 6'2", what percentage of people can fit, and how many people are we saying, sorry, you can't be an astronaut? And so, heart's broken, right? This is, if you didn't want to be a basketball player, you might have wanted to be an astronaut, and it doesn't happen, all right? So it's okay. So 5'4", 6'2". So we want to know over here. So our picture, we've got. So it's always very helpful to draw a picture when you're doing these analyses. Okay. So we've got 5'9.5" in the center, and we're going up to 6'2". All right, or 74 inches. And down here, we're at 5'4". 4 inches, or 64 inches. Okay. And so we want to know what percentage of people can fit in our astronaut suit. Okay. So I'm going to just go ahead and erase this thing to do our math. Okay, so yes. All right, so our mean is still 69.5, and our standard deviation is still 3 inches. Okay. So again, the table only gives you the area to the left. It only gives you the area to the left. So how do you find this area in between? Okay. We're going to break it down into two problems. First, we're going to find the area to the left of 6'2". Okay, so we find all of this area to the left here. And then we find the area to the left of 5'4". Okay, we find this area here. And I say, if you take this area and you subtract off this chunk, what you'll be left with is the area in between. Okay, so you do this area minus this area, then you will be left with the part that you're interested in. Okay, and this is what we want to know. Okay. So I purposely picked 6'2" because we just did it in the previous problem. So here we know that the area to the left here is 0.9332. The area to the left is 0.9332. Okay, so now we just have to find the area to the left of 5'4". So again, the way we do this is we first find our z-score, and we get z is equal to 5'4" is 64 inches. So our y is 64 minus our mu of 69.5 divided by our standard deviation of 3. So we're going to have a negative z-score, which makes sense because we're below the mean. Anytime we're below the mean, we have a negative z-score. We have negative 5.5 divided by 3. What does this come out to? Negative 1.83. Thank you. So we have the cutoff at negative 1.83. And so what is the area to the left of negative 1.83? We go over to the negative 1.8 row, and we go to the 0.03 column, and that is 0.0336. 0.0336. Okay? So the area to the left of negative 1.833 is 0.0336. And we know the area to the left of 6'2", or 74 inches, is 0.9332. And so the area in between is going to be 0.9332 minus 0.0336 So that equals 0.8996. 0.8996. So about 90% of people can fit in our hypothetical astronaut suit, okay? So we're only discriminating against 10% of people based on height alone, okay? So it's not, all is not lost, okay? So this is 0.8996. Okay, so are there any questions on any of the steps that I performed in this process here?
How'd you get that mean again? 69.5?
That was just given to us in the problem, okay? The mean and the standard deviation is just given to us in the description of the normal model, okay? Yes?
This only works if it's a normal model.
Yes, this only works for normal models, okay? So if we have something that's skewed or whatever, has more than one peak, we can't do these calculations. That's very, very important. That's a very good observation, is that this only works for the normal model. If things do not follow a normal model, then we can't say 20% fall less than this, or this is that, and things like that, okay? All right, so we've gone from heights to percentages, okay? Now we can go the other direction, all right? So we might be able to say, if you are 6'2", you're in the 93.32 percentile, okay? But we might ask, I don't know, what, how tall is someone who's in the 10th percentile, okay? So the other question we might ask is, how tall is someone, okay, and by someone I mean US male, all right? How tall is someone who is in the 10th percentile? Okay, and again, our mean is 69.5 and our standard deviation is 3 inches, okay? So here, we're asking kind of a backwards question. So instead of having a height and asking what percentile, we're given a percentile and we're asking what is this height, okay? So the idea here is now we've got 10%, okay? So this person is taller than 10% of the population, or in other words, shorter than 90% of the population, and we want to know how tall is it? So what is the height that corresponds to being taller than 10% of the population? And we still know the center is at 69.5 and that the standard deviation is 3 inches, okay? So this is where it gets a little bit tricky, or just, it's not tricky, but you just have to remember what you're doing, okay? So it still involves z-scores and everything and all of that good business, okay? Except we're looking up the percentile first, okay? So instead of looking up, we don't go here and we don't look up 0.100. We're not looking up 10% as a z-score, okay? We're looking, because these are z-scores, these are not even percents. We're not looking up 0.10 as a z-score. We have to find the area that's as close as possible to 0.1000, okay? So in this zone of the table, so not on the edges, but in the part with all the numbers in it, we're looking up for the number that's closest to 0.1000, okay? So remember, all the numbers in here, these are is the area to the left of the cutoff line, right? So here we had z-scores, and we find the area to the left of the cutoff line. And now we know that the area to the left of the cutoff line is 0.1000. We want to know what is the corresponding z-score. Okay, does that make sense? So we're looking up 0.1000 in the table, and we want to find the corresponding z-score, okay? And I know I'm going to be on the negative side of the table because we're smaller than the mean, okay? And that's because whenever we're smaller than the mean, we have less, our percentile, the area to the left is less than 50%. If we're larger than the mean, okay, our area to the left is going to be greater than 50%. Okay? At the mean, we've got 50%. So here I'm on the negative side of the table, so I'm looking up the area, the value in this part that's as close to 10% as I possibly can get, all right? And the closest I can get is negative 1.28. So the closest I can find is not 10% exactly, but it's 0.1003, okay? And there's two numbers that are really close. We've got 0.1003, and we also have 0.0985, okay? Okay, so these two numbers are the two closest numbers to 0.1000 in the area of the table, okay? And this one is a little bit closer than this one. So I'm going to choose 0.1003, and that corresponds to a z-score of negative 1.28. Okay? All right. Is this okay? All right. So if you have questions, sometimes the switch going from area to z-scores, that some students have difficulty with that. So if you still don't fully understand where I got negative 1.28, ask away, okay? And you'll have a couple homework problems to try this out. Yeah.
If you would have chosen the other number, it would have been 1.29?
Yeah, if we chose this number, okay, if this number was closer to 1.0, then yes, we would have chosen negative 1.29, yes. Okay, so we know our z-score by looking up the area, 10%, or the thing that's closest to 10%. We know our z-score is negative 1.28, and this is equal to y minus mu divided by sigma. It's still the same z-score formula, okay? However, we know what mu is, and we know what sigma is. That's given to us in our definition of the normal distribution. And so we have, so I'm going to replace those, and we got y minus mu, or y minus 69.5, divided by sigma, which is 3. Okay, so here I'm just going to rewrite this. I've got negative 1.28 is equal to y minus 69.5 divided by 3. Okay, so now solving for y, it's just an algebra problem. We multiply both sides by 3. Okay, and so I have 3 times negative 1.28 is equal to y minus 69.5. And now I add 69.5 to both sides. So I have 3 times negative 1.28 plus 69.5 is equal to y. All right, and so we just have to punch this into the calculator. 65.66 is equal to y. Okay, so these were just algebra steps, just multiplying both sides by the denominator and then subtracting off the difference here. Okay, and so in the homework videos, I kind of go through the algebra steps quickly, and I hope that's okay. If not, just look over some of your old algebra notes and brush up on some of those skills. Okay, and so here we can now answer the question: how tall is someone who is in the 10th percentile? That person is going to be 65.66 inches, or 5 foot 5.6 inches, or 6 inches. Okay. Okay. Is that any questions on this step going the other direction? Okay, and then so you'll have a couple homework problems going through this. There's one that's going to ask something like, what is the range for the middle I don't even know, 60% or something like that. So it says, what is the middle 60%? Okay, don't get scared, all right? If it says middle 60%, that means you've got 30% on this side, 30% on this side, okay? And basically, if you got 30% on this side and everything on this side is going to be 50%, that means we've got 20% down here and 20% up here. So the middle 60%, we've got 30 on each side and then 20% in the remaining tails. So then this is just a matter of finding what is the corresponding height or whatever, the 20th percentile. And this is also the corresponding height of now 30 plus 30 plus 20, or the 80th percentile. So it's no different than what we've just done here. It's just you got to do a little extra thinking at the very beginning of the problem. Okay? Yes, we have a question.
What did you do when you got the 65.66 and then?
Yeah, and that's so we got 65.66. So that is the y. That is the height. So that's just the answer to our question. How tall is someone who is in the 10th percentile? That person is going to be 65.66 inches, okay? Or if it was, I don't know, how many, I don't know, what is the pulse of somebody in the 10th percentile or something, and it would be some other number, right? Or if woodchucks could chuck wood, followed a normal model, then we could say the amount of wood the 10th percentile woodchuck, so could would be, I don't know, 10 cubic feet. I have no idea, all right? Okay, and so that covers the normal model, and that takes us to 9:47. I hope your guys' brains are okay and able to digest. It was a lot of material, you know. Every time I go over each day's lesson, I'm like, wow, we got a lot of material to cover. So I hope that's okay. Again, review your notes and read the book, do the homework. Okay, please don't just wait till the day before the homework's due and then hope all of this knowledge comes back, okay? I promise if you don't look at this stuff for 6 days straight, it'll just be gibberish when you look at it again. So look at it on a regular basis. So.